Okay, if you missed this lesson 7.08, we talked about two different things, limits at infinity and infinite limits. So let's start at talking about limits at infinity. We can see already that we are tasked with, taking the x value as we approach infinity, which kind of brings up our first question, our first thought. How do we take the limit at infinity? Normally what we would try to do is plug in that x value and see what we get. Well, we can't plug in infinity, right? We really have no number to work with. So you might be thinking about plugging in a number that's really close to infinity, right? Maybe a trillion. I don't know, the biggest number you can think of, but really that's not even close enough to infinity to even plug in to get an accurate enough idea. So what we have to do is we have to think a little bit differently about this problem. Instead of plugging in infinity, we want to think really about this function's end behavior. So as we go all the way to the right, so whatever function that we're talking about, we want to know where our graph is going. And if you could just imagine kind of those rational functions that we deal with, they usually end by going all the way up to infinity, all the way down to negative infinity, or they flatten out at some horizontal asymptote, right? Those are really our three options. So we're just going over how do we distinguish which one of those it's going to be. So what we do here is, you may remember from polynomial functions and end behavior of polynomial functions, we take the leading term. That leading term is really going to be what shows us the end behavior of this function. We really only need that leading term because that's really going to dominate the rest of that function. So we have a leading term at the top and bottom of negative 3x squared over 2x squared. And if we can, we always should try to reduce the leading terms of the top and bottom. And here I see I have an x squared on the top and bottom with those leading terms. Those are going to factor out and give us like a 1 whole on top and bottom. And we're just left with negative 3 over 2. Now, after all that factoring, we just have two numbers. Well, that is our limit. That is our answer. So what does that mean? It means that we actually have a horizontal asymptote there, that our function is actually going to approach negative 3 over 2 as it continues on to the right, and it's going to flatten out. And that is one scenario. We'll come back and we'll stamp this in a second of just why exactly we had a horizontal asymptote there. Problem number 2 is, once again, finding the end behavior, right? I'm going to put EB there for end behavior, right? We're going to infinity. I can't plug in infinity. So we're going to try to find those leading terms again. Well, I have a negative x on top. That's really the only variable that's going to be dominant over the 2. And then I have a 2x and an x squared on the bottom. And we're not just choosing one or the other here. We can see that those two things are being multiplied. So let's multiply them. So my leading term of the top is negative x. And my leading term of the bottom is going to be 2x to the third. And once again, we should always try to reduce this. So let's see, I got an x on the top and an x on the bottom. I'm going to leave that negative up top, but the x is going to cancel out, and I'm still going to have 2x's left over. So I'm going to have 1 over 2x squared. So we can see that here this time, we're not left with just like a regular number. We still have an x squared left over. Well, let's think about this. If I were to plug in a really, really big number, like 100, 1,000, 1,000,000, a billion, a trillion, something that is getting very big, very fast. And I were to do 1 divided by 2 times that number right? We would have like 1 over some really, really big number. Plug that into your calculator. 1 over a really, really big number is actually going to be a very, very small number, right? 0.00000, whatever. So in fact, when we plug in a really big number into the denominator, we are actually going to approach 0. So it's going to be another horizontal asymptote. So here we have equals 0. So now we have a horizontal asymptote at y equals 0. A different case, and you may notice something about the difference between this first one and the second one. We'll come back to stamp that in a little bit. And this third one is even more unique in the fact that it has a 2x to the 4th over x. So we have 2x to the 4th over x. These are my leading terms. I'm again finding my end behavior, and I'm going to reduce again. Then one of those x's cancel out, and I'm left with x to the 3rd here. So I'm left with just 2x to the 3rd. Now this is no longer a fraction. This is just a polynomial expression. And remember, this is the type of thing that we used to have a chart for, right? Remember that chart where we used to talk about positive or negative and even or odd? And once we found out what it was, we would come down and we would annotate the end behavior of that polynomial function. You have this in your notes. So this cubic function x to the 3rd, to the left is always going to go down, but to the right is going to finish up. So we're talking about to the right here, right, as we go to infinity. So what that tells me is here that our limit for this function is equal to infinity. All right, so now let's stamp kind of our general understanding of each one of these. So for this first one, what did we have? We had x squared and x squared that reduced to -3/2, right? So basically, if the powers are equal, and I'm talking about the powers of the leading terms, right? If the powers of the leading terms are equal, we'll have an HA, right? And that HA just came from what was left over, right? That -3/2, those coefficients. All right, we also had an HA, a horizontal asymptote, for the second problem. This was different. This is going to be basically if a greater power, in denominator of our kind of leading terms here, HA is always going to be y equals 0, right? And I kind of demonstrated how we're going to approach 0 if we plug in a very, very big number into the denominator of a fraction. Okay, so the difference is one of these has equal powers. We just divide the regular numbers. Part B here has a greater power in the bottom, so that's automatically going to be 0. No math needed. It's automatic. All right, and then this last one, we can see that we actually had a greater power on top. So if greater power in numerator what did that mean? We had to sketch our end behavior. I reduced it, and then we sketched our polynomial end behavior. And that's going to tell me where our function is going. Okay, and I can get this from our old notes. So that's limits at infinity, which really is just a whole lesson on end behavior of functions and annotating leading terms. All right, I'm going to clear this, and I'm going to talk about our other type of limit today, which is infinite limits. Okay, infinite limits are going to be a little bit different. They look a little bit different to start. So let's take a look at this first one. We are no longer taking the limit at infinity. We're taking the limit at 3. Well, I'm going to rely on my old strategic way of doing these, which is to actually just plug in a 3 and just see what happens. And I'm going to get 3 plus 1 over 3 minus 3. And in something like this, I get 4 over 0. And this screams to me that something went wrong. We cannot divide by a 0. No, it is not 0. Type it into your calculator. You see 4 divided by 0 is error, undefined. Can't do it. Can't divide by 0. Your calculator will say something back to you. So something happened here. And this is significant. This tells us a message. This tells us that something is happening in our function. This is undefined. And the message that it's trying to send us about this rational function is that there's a vertical asymptote. So anytime that you see some number over 0, when you try to take that limit, you're going to get a vertical asymptote. Well, remember what those look like, right? Some vertical line that our graph doesn't cross. It either goes all the way up or all the way down as it approaches it. Right? Could be any one of those things. So what we need to do is we need to find that limit still, because a limit could still exist in a problem like this as long as both sides of that vertical asymptote are approaching the same thing. So that's what we're being asked to do. Let's find the left, let's find the right, and let's find that two-sided limit of this function. Okay, so how do we do that? Well, we already tried to plug in 3, and that didn't work. Okay, so what do we do instead? Well, this is what we do, we call the sign test, where we can't plug in 3, so we're going to plug in numbers very, very close to 3. So let's just think about our number line. I mean, obviously on either side of 3, we've got 2 and 4, but we want to get even closer than that, because the closer we can get to our vertical asymptote, the more we'll know about the direction our graph is heading. So we're going to choose numbers that are like 1 decimal place away, like 2.9 and 3.1. Okay, 1 being just to the left and 1 being just to the right. So now we're going to use these to find our left-sided and right-sided limits. So let's just take a look. From the left, we're going to use 2.9, and from the right, we're going to use 3.1, just thinking about your number line. So this first one, since there's that little minus sign there, that tells me that that's going to be my left-sided limit. So this must be my left. So what am I going to plug in? 2.9. And now remember that with vertical asymptotes, we're all the way up or we're all the way down. There's only two answers here. It's going to be infinity or negative infinity. That's all we're trying to figure out here. So you could plug this into your calculator and get a very big or a very small number, but we really just need to know, is it really big and positive or is it really big and negative, right? Which way is this going? So 2.9 plus 1, I just know that's going to be some kind of positive number. And 2.9 minus 3, well, 3 has a greater absolute value. So this is going to be some kind of negative number. Well, positive divided by a negative is a negative. So therefore, our answer is negative infinity. Okay, if you were to actually do this out, I think you'd actually get 3.9 divided by 0.1. You get like negative 39, right? And if you plugged in 2.99, you get like 399, right? So, or negative 399. So you get closer and closer to negative infinity. We go continuing to go down. That is our left-sided limit. So if I were to get a picture here, here's our vertical asymptote. Well, I'll draw that later. The next one is talking about to the right. So we're going to use that 3.1. And let's just do that work real quick. We're going to get a positive, or this time a positive. So that's going to tell me we're going to get a very positive number. In this case, I think we'd get 41 as our answer here, right? It's going to be going up very fast. So this is a positive infinity. So now when we talk about our two-sided limits, remember that two-sided limits just tell us, okay, do our limits agree? And if they do, what at where? So we have a vertical asymptote. And if I were to think from the left, we said that as it got very close, it went very far down. From the left, it's going down. And from the right, it's going up to negative infinity, right? So this is a picture of what's happening here. This is a picture of our vertical asymptote. And so remember that a two-sided limit has to agree. The left and the right have to be equal. If the left and right aren't equal, which clearly they are not, our limit does not exist, right? So our answer here we would put is DNE. The limit does not exist. So we can see here, we call these infinite limits because these are limits at vertical asymptotes. And whenever we have a vertical asymptote, we're going to be going all the way up to infinity or all the way down to infinity. How we decide that is by plugging in numbers that are very close to that number in question. So since 3 was our vertical asymptote, we plugged in 2.9 and 3.1 to find out if we were going up or going down. And then we can kind of put those together to see what our two-sided limit would be. Now, if they just happen to both agree, like let's say they're both going up to infinity on both sides, well, then our two-sided limit would be infinity, right? Because they have to agree. But in this case, it's DNE because they don't. Go ahead and go to 7.08. Go to that exit ticket. Try both of those on your own. Submit that for classwork. Make sure to show every step. Show your annotations. Look at all the work that I've done. I expect you to do just as much on your own. And good luck.